We're going to move out of thermochemistry and move straight into kinetics. Kinetics is prepping you for your second year chemistry class. And it's a pretty simple unit where we're just understanding how molecules react with each other in terms of speed. So the first part is collision theory. Now there's two parts of collision theory. The first part is that all molecules must react together with a minimum amount of energy, and we call this the activation energy. And it must be, and it is absolutely required. And they also must have the correct orientation or geometry. Now, both requirements must be fulfilled for this to happen. So this is a good representation of activation energy in an energy profile, right? This is the profile right here. The activation energy is the hump right here. And also for the orientation, remember that this one reaction will work, but this one will not, because for the reaction to happen, the ethene molecule, this would be ethene, the white circle needs to point directly right at it. It won't work if any of these other ones are lining up in a different way. It's just not going to happen. Now, another term to understand is the activated complex. If the collision of the reacting molecules in a reaction have high enough energy to break bonds and the orientation of the molecule is correct, a transitional structure forms as old bonds break and new bonds form. This structure is known as the activated complex. The activated complex is very unstable and short-lived. It will either reform the reactants or form the products of the reaction. So the activated complex lives up at the top of the hill. So as we push the reactants up, the stone could either roll back, that would be unfortunate for this man, or it could roll downhill and become products. Now this isn't a very good example because the stone is still a stone before and the end. So you could have this one right here. Now this one's still not a good. This one's a good example because the nitrogen and the carbon can actually switch places. But what's going to happen is we have the activated complex right here where the molecule is actually kind of flipping around. It's the intermediate kind of something that exists for just a split second. If we have a diatomic molecule and two particles right here, they can kind of fuse together and again exist for about a split second and then end up right here as products. Or you can either have this very nasty nitrogen monoxide molecule can steal an can steal an oxygen from ozone, and then we have the activated complex at the top, and then we have NO2 over here with an oxygen molecule. So the ozone has been destroyed. Well, this NO2 can actually pick up another oxygen, can destroy another ozone molecule, or it can dissolve in the water and become acid rain. So that's some pretty nasty stuff. This is really bad for the environment, and we can get more into that later if you want. So a reaction mechanism is a series of steps that takes place during the course of a reaction. Now that we have an overall reaction here called the master reaction, I don't call it that, I call it that, but it's not the real way. And we have a series of elementary steps. So these steps are proposed. These are theoretical steps for what we think is how we're getting to here. How do we get from this part over to this part? So what you are going to do is you're going to form intermediates. You're going to form something and then you're going to consume it. All right? And then it should be the mechanism. This is a mechanism, by the way. The whole thing is a mechanism. Should add up to the overall reaction. Now this is the overall reaction. If the mechanism adds up, then it is going to be plausible. So pause the video and see if you can identify the intermediates. Okay, never mind. I know you didn't pause the video. So there's a good intermediate here, and NO2 is produced, but it is also consumed. NO3 is produced and also consumed. NO is produced and also consumed. And if you see right here, we have N2O5 and NO3 on the left side. See how they add up? We have O2 right here, and we have NO2 and then 2 NO2s make 3 NO2s, right? So wait, what if I took away this one and did this one right here? Is that still plausible? Yes, it is. That's why we can still only really consider these theory. We're not entirely sure how these work because, again, they happen very, very quickly. So we can really only measure the reactants and the products. Example 18, follow along in your notes. The following mechanism has been proposed for the following overall reaction here, and we have our 3 elementary steps. So let's see if this mechanism works for this. What we'll do is I'll usually just draw a line, and I try to just take everything that's on the left side and just write it down, and then put an arrow, and then put everything on the right side and write it down. So I'm going to do that virtually for you. And you have everything just laid all out. Now what you are going to do is just like math. You're going to cancel everything that is the same on both sides. So we have N2O2 is the same on both sides, and also N2O is the same. Now I will then reduce that into that. So now I have an overall reaction, and this looks kind of similar to this one, but we have H2 and H2. Well, that's 2H2, right? So that's still the same as that. And then we have H2O, N2, and then H2O. Well, let's combine the 2 waters, and then that's still fine. So yes, this does add up to the overall reaction. Now, to identify the intermediates, you would identify the things we crossed out, basically. It's the things that are produced, but then consumed. All right. Now, so the same example, but just with a little twist. Now, what is the rate limiting step? Which one is going to determine the rate? Well, to explain that, I'll show you this. If I was to pour a beaker right here, and I had a small funnel that moved really slow, and then the bigger funnels that move really fast, which one do you think is the rate limiting beaker or rate limiting funnel? It's going to be the slow one, right? No matter where it is, if it's the first step, the second step, or the third step, it's always going to be the one that limits the rate. It can only move as fast as the slow step. So the slow step is always going to be the rate limiting step. Just remember that. All right, and if you want to get a good representation of that, just Google the I Love Lucy candy store or candy factory clip. That's always a good example of the rate limiting step. I hope you all have a great day.